Good morning, good afternoon, and good evening. Welcome to the Crazy Hat Chemist. So here we go with another awesome video. Today's video, what is it going to be? That's right, it is nuclear chemistry worksheet, general chemistry, II, or number 2. Before you watch this video, you need to do a couple of things. Number 1, you need to watch nuclear chemistry worksheet GC1 and do that one first. And you also need a periodic table of the elephants. Wait, did I say that correctly? Nope. I mean a periodic table of the elements. That's right, not the elephants. All right, here we go. Just a little chemistry humor here to start off the morning, the afternoon, or the evening. I'm not really sure what it is for you. So without further ado, let's actually keep on going here. So here's what we're going to do. We're going to write the equations. We're going to write the equations for the following. Number 1 is polonium-210 undergoes alpha decay. All right, so what we're going to do is we're going to find polonium on our periodic table, and it's going to be close to that average atomic mass of 210. So let's see if we can find polonium. This is 207, there's 208, there's 209, there's 210, and polonium is in this category somewhere. There is polonium. Awesome. And the symbol for it is PO, and it is atomic number 84. Okay, we are using the standard nuclear notation here, which is AXZ. Standard nuclear notation means the following. The A is called the atomic mass. Okay, and the atomic mass is actually equal to the sum of the protons and the neutrons. And then this is right here, Z is the atomic number, which is equal to what? The number of protons. That's right. Awesome. All right, so what we're going to do is we're going to write the equation for polonium-210. And so we're going to write PO. That is the X here. And then we said that it is 210. So that is the mass of 210, the atomic mass. And then we looked on our periodic table. We found polonium. It is element number 84. So that is atomic number 84. So we're going to write an 84 right there, just like that. That looks beautiful so far. Hopefully you're going well. All right. So the next thing we need to know about this is that we need to draw an arrow here, just like that. These are all what are called decomposition reactions. A decomposition reaction starts with one reactant, of which we have here, to the left of the arrow, and then we're going to end up with 2 or more products. In the case of this entire worksheet, we will have 2 products. It's going to undergo alpha decay. So we're going to write the symbol for the alpha and the numeric values. That's a 4 and a 2 and the alpha symbol, just like that. Perfect. You need to actually have that memorized, so hopefully you have done that, and that would be most helpful. All right. All right, now what we're going to do is we're going to do the math associated with this, and so we're going to come up with the AXZ that's on the other side. All right, so here we go. And what is that AXZ? So the A, the X, and the Z, I'm going to replace those with the numeric values that are associated with this. And that's what we're trying to do here on this problem. So how do we do that? We are going to do the following. We're going to take our 210, that's equal to 4 plus A. A is what we're solving for mathematically. So that's 210 minus 4. So that means that this A right here, I'm going to replace that A with the 206. 206, just like that. All right, perfect. Now what we're going to do is we're going to take this 84. 84 is equal to 2 plus the Z. And so we're going to do the 84 minus the 2, and then we're going to get 82. So that takes care of the Z. That will be an 82, 82, just like that. And then 82 tells us what element it is. So that 82 is the atomic number. That's the Z. I'm going to find 82 on our periodic table. There is 82, and then it's most certainly Pb for lead. So I'm going to write Pb right here, just like that. Fantastic. That's how we do this. All right. Cool. Let's go for the next one. I'll do this one in a different color so that you can clearly see this. This is americanium. That is 243. So I'm going to look on my periodic table. I'm going to find an element that is close to a mass of 243, and it just so happens to be 243. That's americanium. And that is element number Z of 95. So that is AM 243. And then it was element number 95. This is going to undergo alpha decay, just like the last one. That's a 4A2, the alpha symbol. And I'm going to have to write out what the A, the X, and the Z are for this as well. So let's see if we can do that. So 200, we're going to follow the same pattern that we did on this previous one. That's 243 is equal to 4 plus what number? And so we're going to type in 243, and we're going to subtract 4 from that, and we're going to get 239. Then we're going to take 95 is equal to 2 plus what number? So we're going to take 95, we're going to subtract 2 from that, and we're going to get 93, 93, just like that. And now what we're going to have to do is we're going to look on our periodic table. We're going to find element number 93. So what is element number 93? There's 93 on our periodic table, and that's neptunium. That's Np. So that's a capital N and a lowercase p. There we go. You should be checking your work on every single one of these problems. And how do you check your work? 206 plus 4, does that equal 210? That's correct. 82 plus 2, does that equal 84? Yes, that's correct. 239 plus 4, does that equal 243? Yes. 93 plus 2, does that equal 95? That's correct. All right. So that's how we're going to do that. All right, let's keep on flying on this. This is berkelium 248, and we're going to find element number whatever that is for berkelium, but it has a mass of approximately 248. So 247, 247, 251. Oh my gosh, there is berkelium, one of my favorite elements. I don't know why, I just like berkelium. It's element number 97, and it's BK. So it is 248. It is a B and a K, and it is element number 97. Okay, perfect. All right, so and then this undergoes alpha decay, so that's a 4A2, and the alpha symbol there, just like that. It's 248 minus the 4, and I'm going to get 244. That's the mass of my new element that after the decomposition. And it's 97 minus the 2, that is 95. And I'm going to look up number 95 on our periodic table here. And we've actually covered this one already. There's number 95, and that's americanium. So that's AM. Perfect. You guys are doing a fantastic job, hopefully, and hanging on here. That's not too bad. This is radium 228. So we're going to find radium 228 on our periodic table. It has a mass of approximately 228. There's 223, 226, 227. Oh, look, there's radium. It is element number 88, and it's Ra. Okay, so that's Ra, and that is 228, and that is element number 88. Atomic number 88 is going to decomposition to an alpha particle and another element. So that's 4 and 2 with the alpha symbol, just like that, plus. So now it's 228 is equal to 4 plus what number? So that's 228 minus 4, so that's 224. That's the new mass, and it's 88 is equal to 2 plus what number? That would be 86. Now I need to find element number 86 on our periodic table. Let's see if we can do that. Here we go. That's element number 86, and that's Rn for a radon baby. All right, radon baby. So that's Rn, just like that. All right. You guys doing a fantastic job. We're going to scroll this on up here just a little bit. By the way, these are all alpha decays that we have done, so you should understand the pattern for the alpha decay. The other way, just so that you know, instead of writing this for the alpha particle, there is another way to write it. That's a 4, a 2. The numbers don't change, and it is a helium nucleus. That can be replacing that little alpha symbol. But it's most commonly, if you can actually give it a try, write that alpha symbol. It's probably much better. Shows that you know a little bit more chemistry than the average Joe. All right, not that Joe doesn't know chemistry. So, all right, let's scroll this on up here, and we're going to do some more problems here. And here we go. This next one here is strontium 90 undergoes beta decay. So we're going to do some different kinds of decay, and you're going to see the difference between the alpha decay and the beta decay. So we first need to find strontium. Its approximate mass is 90. There's an 85, there's an 87, an 88, a 91, and there most certainly is strontium. That's SR element number 38. So it has a mass of 90, it's element number 38, and it's SR. Beautiful, just like that. It's going to undergo a decay, except this time it's a beta decay. So that's a beta symbol right there with it's actually a capital B with like a little tail. The numbers are 0 and -1 plus. And now we're going to do the same thing that we did before. I'll do this first set just like I did on the first set with a pencil. This is an A, this is an X, and this is a Z. So I'm going to be solving for the A. I'm going to solve for the Z. After solving for the Z, I will be able to obtain the X from our periodic table. So it's going to be 90 is equal to 0 plus what number is A? And this should be pretty easy here. That would be a 90. So the atomic mass does not change with a beta decay. So this is a 90, just like that. Then down here, it's a 38 is equal to -1 plus Z. Okay, and this is the one that throws students off for just a little bit. So hang on to your horses on this one. Okay, so how you do this is you add 1 to both sides, and this is going to be a 39. So this Z is going to be a 39. So I'm going to erase this Z. I'm going to have atomic number 39. Now what we're going to have to do is we're going to have to look up element number 39 on our periodic table. That is right next to the strontium. There's element number 39. That's Y for yttrium. All right, so I'm going to replace this X with a Y. Capital Y. Here we go. There we go. There's our first beta decay. Beautiful. And then just like what we did right over here, this is the beta symbol right over here. The other way to write the beta symbol is a 0, a -1, and an E just like that. That is the alternate way to do that because really a beta particle is an electron that is being removed. Okay, all right. If you want to know more about how an electron can be removed from the nucleus, then you're going to watch my videos in honors chemistry on nuclear chemistry. And I go over why that is. It's actually a neutron that decays into a proton and an electron. The electron is the particle that is ejected out of the nucleus because electrons do not belong in the nucleus. That's how that goes. All right, this next one is technetium 99. So let's find that here on our periodic table. That is right here, and that's TC, element number 43. So TC, it's 99 is the mass, and the element number is 43. It's going to undergo a beta decay. The numbers are 0, -1, and there's the beta symbol, plus. So 99 is equal to 0 plus what number? 99. Awesome. All right. And then 43 is equal to -1 plus what number? That would be 44. Awesome. Everybody looking good on that one? Just make sure that you got that -1. This is not really tricky, but not supposed to be tricky or anything like that, but could be for some students. Just make sure that you do the backwards calculation to check your work. So 99 plus 0, does that equal 99? The answer is yes. 44 plus -1, that's 44 minus 1, does that equal 43? The answer is a yes on that one too. So what we're going to do is we're going to find element number 44, and that's Rutherfordium, or Ruthium. That's Ru. So that's Ru, just like that. Perfect. Let's do the next one. It is carbon 14 undergoes a beta decay. So carbon 14, the mass is 14. We're going to find carbon on our periodic table. That's right here. There's carbon. It's element number 6. It has a capital C and a capital C only. So a C, it's element number 6. It's going to undergo beta decay, 0, -1, and the beta symbol plus. 14 is equal to 0 plus what number? That would be 14, so the mass does not change. A 6 is equal to -1 plus what number? That would be 7. So the atomic number changes. We're going to find atomic number 7 on our periodic table, and that is right there for nitrogen, and that is a capital N. There we go. That is for nitrogen, just like that. Beautiful. Okay, we got a few more here to do, no doubt. We have nitrogen 13 undergoes a beta decay. An I right there. Okay, so nitrogen, we have nitrogen 14 and there's nitrogen 13. So we're going to say 13, it's element number 7 and it's an N. And it's going to undergo beta decay. And there's our beta symbol. 13 is equal to 0 plus what number? 13. And 7 is equal to -1 plus what number? That would be 8. So what is element number 8? Element number 8 is, oh yes, none other than O for oxygen. Okay, so that would be just like that right there. Perfect. All right, now what we're going to do is we're going to do a couple others that are just slightly different here. So I'm going to keep some of the alphas, some of the betas, and now we're going to do some gamma decay. So we got cesium 137, so we got to find cesium on our periodic table. Here is cesium, that is a CS, and a 55 is the atomic number. So it's a 137 for the mass. It is element number 55. And it is a capital C, lowercase s. It is going to undergo gamma decay this time. So there is the gamma symbol. It looks very similar to the alpha symbol, except it looks like a fish swimming down to the bottom of the ocean here. And so that's the numeric values for that is a 0 and a 0. So 137 is equal to 0 plus what number? 137. This is pretty simple. 55 is equal to 0 plus what number? That would be 55. And then I'm going to write the symbol of this element, which of course is the same element because the atomic number does not change, so that's CS. I'm going to put a little asterisk next to this one here, and this is lower in energy than the reactant was. So just so that you know, it looks like, wait, I'm getting the same thing. Yes, that is correct. However, this product is lower in energy than this reactant was, and that's what happens. The next one is cobalt 60. So we're going to find cobalt on our periodic table. It is element number 27. It is a capital C, a lowercase o. The capital C, lowercase o, and that is 60 for the mass and 27 for the atomic number. It is undergoing gamma decay. That's a 0 and a 0, and the little fish going down. 60 is equal to 0 plus what number? That would be 60. 27 is equal to 0 plus what number? 27, and we know 27 is for cobalt. And again, this element here of this isotope is lower in energy. All right, so I'm hoping that you see there's a difference between the alpha symbol and what occurs, the beta symbol, what occurs, and the gamma symbol and what occurs in terms of decay processes. All right, so now what we're going to do is we're going to keep on going. We got more to do. Don't go away. We got more to do on this one. And what we're going to do on this next one here is we're going to combine some of the things that we have just learned into one fell swoop. Okay, so here we go. We've got three problems to, well, no, actually, we're going to do two problems here. Okay, we're going to start off with Neptunium-237, and it's going to undergo a decay series, and that will be an alpha, a beta, an alpha, and a beta decay. So we're going to find Neptunium-237. Where is that? That is right here. There's Neptunium, and it is 237, and it's a 93 for the atomic number. So 237, that's an NP, and it's 93 for the atomic number. It's going to undergo a series of decays. Okay, and so the first decay will be an alpha particle. That's alpha is 4 and 2. Then a beta. Notice I'm not going to write out the product and then do the next one and a product and the next one. I'm going to do this all in one fell swoop. A 0, a -1, and the beta symbol, plus, so that's the alpha, the beta, now the next alpha, which is a 4 and a 2, and the alpha symbol, check on that one. We have another alpha, 4 and 2, alpha symbol, check on that one, plus a beta, which is a 0, -1. And now what we're going to do is we're going to solve for the AXZ on this one here. So it's 239 is equal to 4 plus 0 plus 4 plus 4 plus 0 plus what number? So that's 4. So the numerator, excuse me, up here is 4 plus 4 plus 4. That's 12. So I'm going to have 239 minus 12. And so I'm going to have 227. Perfect. That is the mass of my new isotope. Then it is Neptunium, and that is element number 93. I'm going to have 2 plus -1 plus 2 plus 2 plus -1. And so this total down here of all of these here is a total of 4. So I'm going to have the 93. I'm going to subtract 4. I'm going to get 89. I'm going to find 89 on our periodic table, and that is right here, 89 actinium, that's AC. So I'm going to write AC just like that right there. You should be able to double check this, and you should type in 227 into your calculator, plus 4, plus 4, and plus 4 again. And what should you get? 239. You should type into your calculator 93 and sorry, 89 rather, minus 1, plus 2, plus 2, minus 1, and plus 2 again, and you should get 93. All right, fantastic. All right, this next one is uranium-238. It's going to undergo a decay series as well. And so we're going to write down uranium first. Uranium is right here, right next to Neptunium. It is element number 92, and it is a U because I love U. So 238, U for uranium. Okay, it is element number 92, and it's going to undergo a decay series. The first one is going to be alpha. That's a 4A2. There's the alpha symbol. Then a beta. That's 0, -1, a beta symbol. Another beta. That's a 0 and a -1. That's the beta symbol. An alpha, 4 and 2 for the alpha. Another alpha, 4 and 2 for that alpha. Another alpha, that's 4 and 2 for that alpha. Another alpha yet, a 4 and 2, and that's an alpha. And then the beta, finally, 0, -1, and a beta symbol. All right, so we're really, really close here. We got a lot here to accomplish on this one. So we're going to type in here in our calculator 238 is equal to 4 plus all these numbers here. So we got 4, 8, 12, 16, right? So 24. So got 1, 2, 3, 4, 5 of those. And that's, whoops, sorry, that's 20. 4, 8, 12, 16, 20. So that's going to be 238 minus 20. That's going to be 218. Just going to have barely enough space here to write this down on our paper. I think we're going to have to zoom on out just a little bit. And now we have 92, and there's a 2, There's a -2, so that's just a 0. And I got a 2, a 2, a 2, a 2. And so that will be 2, 4, 6, 8 -1. So that's a 7. So that's a 7 total. So that's going to be 85. And we're going to just do a double check here. 85 -1 plus 2 plus 2 plus 2 plus 2 -1 and plus 2 again, and we should get 92, of which we do. We're going to check on the top here. We got 218 plus 4 plus 4 plus 4 plus 4, and finally plus 4 again, and that's 238. We're going to look up on our periodic table, find element number 85. Where would number 85 be? Well, let's see if we can find that. It's astatine, it's 85, that's AT, just like that. So that's AT. Perfect. All right. Now we're going to do the next thing over here. We're going to do the next thing, which are half-life calculations. All right. So let's see if we can scroll this on up and we can do some half-life calculations. So we've done 2 decay series. So just to summarize, we've done some alpha decays, we've done some beta decays, we've done some gamma decays, and then we've done 2 decay series. So now what we're going to do is we're going to do some half-life calculations. But before we do that, we need a word from our sponsor. And our sponsor for today's video, unlike all the other videos, is I am the Crazy Hat Chemist. So please, you know what to do. Give me a subscription. I would greatly appreciate that. Please hit the subscribe button. Please give me a like and pass this on to all your friends so that you know where is the best place to learn the correct chemistry. Simply and clearly. All right, so now what we're going to do is we're going to find out how much cobalt-60 will remain of a 12-gram sample after 8 half-lives. Okay, and there's a number of different ways of doing these problems here, but I'm just going to show you one. I'm going to do like a little T chart here, which will be a horizontal section since that's what we have. We're going to have amount, and then we're going to have half-lives. So the amount that we start off with is 12 grams, so 12 grams. And that is at time of 0 half-lives, okay? And so I'm just going to draw a line right there. And then what do I do from this point to that point? I'm going to add 1. What do I do from here to here? We're going to divide by 2. Okay, and then we're going to get those numbers. So 0 plus 1, that is a 1. 12 divided by 2 is 6. So I got 6.0. Okay, now what we're going to do is we're going to keep on doing this. We're going to add 1 in this column. In this column, we're going to divide by 2. Okay, and then we're going to keep on going until we get to 8 half-lives. I'm going to stop when I get to 8 half-lives. So this is a 2 right there, and then this is a 3 right there. Okay, I'm going to add another 1 to this column. This is a 3. And this is a 1.5. I divided the 3 by 2. I'm going to add 1. I'm going to get 4. We're like almost halfway there. Divide by 2, 0.75. Then add 1 and then divide by 2, 0.375. We're getting closer here. We only have a few more to go. This is 6 half-lives. And it is 0.1875, and it's 7 half-lives, and that is 0.09375. And then finally, the one that we're looking for, 8 half-lives, and that is 0.046875. So I'm going to highlight that. That is actually in grams. I'm not looking at significant figures here at this moment in time, but that's our answer right there. All right. I'm going to show you an alternate method of doing this same problem. So let me show you an alternate method, and hopefully that will work for you as well. Let's give that a try. So, given that alternate method a try, let me show you that here real quick. So the alternate method is a different equation. So I'm going to slide this up here just a little bit so that we can see all of this. All right, so the alternate method here is the following. 1/2 to the power of the number of half-lives times the original is equal to the amount remaining. All right, so here we go. Let's see if we can do this. So in this case, it's 1/2 to the power of the number of half-lives. How many half-lives? There were 8 half-lives. What was the original amount? 12.0 grams. We're going to type this into our calculator. That's 1 divided by 2, which is 0.5, to the power of 8, that is 0.0039. And then I'm going to multiply that by 12, and I'm going to get 0.046875, which is the same number that I got right there. Perfect. That's an alternate method of doing it in one step. All right, let's give the next problem a try. We're going to try it with both methods here and see if you can get that here. Okay, here we go. This next one is how much cesium-137 will remain of a 28-gram sample after 12 half-lives. So we're going to do the same thing that we did on the last problem. We're going to start off with an amount and half-lives. We're going to draw a little table here. We're going to try to do this a little bit smaller because there's many more half-lives. Well, we're doing the same process. So we're starting off with the 28 grams and 0 half-lives. Okay, so what we have is our 28, and then we're going to divide that by 2, and that will be 14. How many half-lives? 1. And what did I do is I added 1 in this column. I divided by 2 in this column. So I'm going to add 1 in this column and divide by 2. Okay, I'm going to take that 14, divide by 2, and I'm going to get 7, and that's the amount at 2 half-lives. So what did I do? I added 1, and over here I divided by 2. Okay, so I'm going to continue that process. This is 3.5 and 3 half-lives. And this is 1.75 and 4 half-lives. This is 0.875 and 5 half-lives. This is 0.4375 and 6 half-lives. And this is 0.21875 and 7 half-lives. It's going to be a lot of half-lives here, folks, and a lot of space. And this will be 0.109375 and 8 half-lives. This is 0.054685 and 9 half-lives. 0.02734. There are more numbers here, and that's 10 half-lives. 0.01367, and that is 11 half-lives. We have one more half-life to do, and that will be 0.00683597375, and that is 12 half-lives. And that is our answer. So I'm going to highlight that. That is the amount, and that is the number of half-lives. And that's in grams. Okay. Now, what I'm going to do is I'm going to show you the alternate method of doing this problem. It is 1/2 to the power of the number of half-lives. In this case, it's 12. The original amount is 28.0. So I'm going to do this in my calculator here. That is 1/2 to the power of 12 times 28, and that will be equal to 0.0068359375 grams. This is the same answer. That's right. Okay. All right. That is awesome. All right. Now what we're going to do is we're going to do another one here. We're going to do our last problem. And what we're going to do is All right, and I'm going to show you this same process right here with this last problem. So because the number of half-lives is 15, okay, 1/2 to the power of 15 times 5.4 grams. Okay, and if you want to, you should do this little table and you should be able to get the same number that I'm going to get here. So it's 1/2 to the power of 15 times 5.4, and that will equal the following number. 0.123 zeros right there, because that will be 1, 2, 3, and a 4. 1, right, because this is times 10 to the negative 4. 1, 2, 3, 4. So 0.0001647 grams. That is unbelievable. That is fantastic. Okay. All right, so let's see, make sure that you do that. That is 1/2 to the power of 15. Why? Because it's 15 half-lives times the initial amount. And then this is how much remains after 15 half-lives. Perfect. So I'm hopefully you enjoyed that video. Again, please give me the subscription. I greatly appreciate that. Pass that on to all your friends. This was none other than the Crazy Hat Chemist, and that's me. And let's zoom on out here. And here is our almost the entirety of this worksheet right here. Okay, I am the Crazy Hat Chemist, and hopefully you enjoyed that video. This is awesome here, folks. I will see you next time for more crazy videos. Love ya. See you later. See you later, not nader. Holy moly.